You guys have been looking at limits for quite a while in this class, and so I just wanted to start out this class by having you kind of think about it and explain different scenarios where a limit would not exist at some value x equals a. And so you guys had some time to think about it and expand and type some things in the chat. And so here is what has to happen in order for a limit to exist. And I don't want the other piece. Actually, when I pulled the other piece over, it was the same thing. So let me just get rid of that. Okay, so for a limit to exist, the following has to hold. A limit, existence of limit, I'm sorry. The limit of f as x approaches a may not exist. And we know that. And you guys gave me some different scenarios. So one possible scenarios is if f of x becomes infinitely large in magnitude, positive or negative, as x approaches the number a from either side. We say that the limit as x approaches a of f of x equals infinity, or x approaches a, that limit of f of x, is equal to negative infinity. In either case, those limits don't exist. So basically, we were talking about asymptotes, vertical asymptotes in the class before this. And so what this is saying is if we're coming into the left, it could be shooting up to positive infinity and to the right to positive infinity. Or the other case scenario is they're both shooting downwards. So they're both heading in the same direction, but they're never coming to one particular y value. So there's an example what that might look like. It could be a little different. So that's number one. Two, if f of x becomes infinitely large in magnitude, positive as x approaches a from one side, and infinitely large in magnitude, negative, as x approaches a from the other side. So basically, they're just heading in opposite direction. One is going to be heading upwards as we get closer and closer to x equals a, and one is going to be shooting downwards. So it's maybe something like this. And then the last case in which most of you are saying if the limit as x approaches a on the left of f of x gave us a value of L, the limit as x approaches a on the right gives us a value of M, and those values L and M don't equal, then the limit doesn't exist. So in that case, there's a couple of things that could happen. So here's A, we're coming in on the left and we're coming into some value of L. Maybe like this, and then a jump over here. Okay, so here would be a case where it doesn't exist. So looking at limits as we're going off to infinity. So we started to look at that and we were talking about horizontal asymptotes. I want to say yesterday, but it wasn't yesterday. So recall, we would say that f of x, let's say, has a horizontal asymptote. At x, I'm sorry, not x. I'm just going to pause. Okay, so f of x has a horizontal asymptote if, as x goes to infinity, or x goes to negative infinity, and or f of x approaches some value. And we can call it, let's call it L for now, L. So another way to write this is the limit in mathematical terms as x approaches infinity of f of x. This gives us some value of L. And so pictorially, we would have some horizontal line at L, kind of imaginary horizontal line. So I'm going to use that imaginary horizontal line and just dot it. And as our graph is going off to infinity, this is getting closer and closer to this y value of L. Okay, so let's say we don't have the graph. We talked about horizontal asymptotes occur if we have a rational function. So it has to be a rational function. So it has to have a quotient. So you have some function on top, maybe f of x all over g of x. And remember, there was 3 different cases, and it had to all do with the degree of the numerator, degree of the denominator. And so degree of the numerator was larger. Let's see, I'm just going to call it n, is greater than, the numerator is greater than the denominator, degrees. Then there was none. If the degree of the denominator was bigger than the numerator, then it occurred at the x-axis, y equals 0. And then if they were the same, the degree of the numerator and the degree of the denominator were the same values, then it was y equals the coefficient, leading coefficient of the numerator, all divided by the leading coefficient of the denominator. Okay, so I didn't technically write as much as I did last time in kind of shorthand just to recall what we were going through. So notice this limit here. If I'm looking at some limit here, as x is going to, it doesn't really matter, positive or negative infinity, it'll go to the same thing, of 1 over x. So basically, if I'm plugging in, and I can look at this with the degree of the numerator denominator, the degree of the numerator is actually 0. There's no variable in the numerator. And so when we're looking at the degree, we're looking at the highest power of the terms of the variable. Well, there's no variable here, so that degree of the numerator was 0. The degree of the denominator, so the exponent on that x, even though it's not written, is 1. So that degree is higher. And so if the degree of the denominator is higher, we say that we have a horizontal asymptote at 0. And so what's happening is that's going off to 0. Which, if you think about it, if you're putting in numbers that are getting really large in the denominator, like 1 over 10, that's 1/10. 1 over 100, that's 1/100. 1 over 1,000, that's 1,000ths. So you're getting closer and closer to 0 as x is going to infinity. Same idea when we're plugging in negative numbers. So as we're plugging in negative numbers, and for x, as x goes to a negative infinity, well, negative 10, so that would be negative 1/10. Negative 100, that would be, right, that's getting negative 0.001, negative 100ths. Negative 1,000, so that's even getting closer to 0. So we can see that this is going to get closer and closer to the x-axis as that goes to negative infinity. And that's pretty much true for any power in the denominator. So for instance, if that had x to raise to some power n, so it was 1 over x to the nth, where n, I'm going to say n is a positive number, because if I had a negative number for n, rules of exponents, if it was in the denominator, would actually bring it up to the numerator. So I'm going to just put on the stipulation that that n value has to be greater than 0. So if this was going to plus or minus infinity of 1 over x to the n, this is also 0. So this rule is actually going to help us to find limits of a rational function as we go to positive or negative infinity. Okay. So finding limits as x goes to plus or minus infinity of a rational function. So the first thing that you want to do is you want to look at the degree of the denominator. So find the degree of the denominator. So again, the highest exponent of the variable down in the denominator. And so once you figure out what that is, you're going to divide, you're going to multiply really by a fancy one. So we're going to multiply the numerator by 1 over x to the nth. Let's say that n, I'm going to just call that n equals the degree of the denominator. So we're going to multiply the numerator by that 1 over x to the n and the denominator by 1 over x to the nth. Once we've done that, we're just going to simplify. Just to recall, we're going to need to use rules of exponents. So recall, if you have the same base, so let me say b raised to the m power divided by b raised to the nth power. Same base division, then we subtract the exponents. So this is b to the m minus n power. So once you've done that, then we can again take the limit. So take the limit as it heads off to positive or negative infinity of f of x, of what we had just gotten above, and use the fact that the limit as x approaches plus or minus infinity of 1 over x raised to the nth power equals 0. So I'm going to look at an example doing this. So we're looking at the limit here, this example, as x is approaching infinity of the numerator, which is x squared plus 2x minus 5, divided by the whole denominator, which is 3x squared plus 2. So if we just went in here and did direct substitution, we would get the form of, well, infinity squared, that's still going to positive infinity, right? Plus 2 times infinity is still infinity. And if I have infinity and I subtract 5, and that's still growing, it's still growing to infinity. So basically, in both of these cases, this is infinity over infinity. Just like 0 over 0 was an indeterminate form, this is also considered an indeterminate form. It doesn't tell us anything about what's going on with a graph. And so this is where you have to go back and you need to manipulate it so it falls out. And so we're just going to use what we were just talking about. Look at the degree of the denominator. And so if I look at the degree of the denominator, so the variable raised to the highest power, this is a 2. So the degree of the denominator is a square. So we want to divide both the numerator and denominator by 1 over x squared. So 1 over x squared, we're going to multiply that to each term in the numerator, all divided by 1 over x squared. We're going to multiply each term in the denominator by that. So when we distribute to each term, sometimes that variable will simplify. So I have an x squared here times 1 over x squared. Well, so that's basically x squared over x squared, plus 2x all over x squared minus 5 all over x squared. Dividing it or distributing to the denominator, I would have 3x squared all over x squared plus 2 all over x squared. So using those rules of exponents, or x squared divided by x squared is just 1. So the limit as x goes to infinity of 1 plus, well, 2x over x squared. That leaves a negative, or give me 2x to the negative 1, or I can rewrite that as 2 over x. Nothing simplifies for that third term in the numerator, so we have 5 over x squared. So the denominator, that 3x squared over x squared's canceled, just leaving you with 3, plus 2 over x squared. And so now when we go in and plug in infinity wherever we see an x, so we have 1 plus, I'm just going to write it this time, 2 over infinity minus 5 over infinity squared, all over 3 plus 2 over infinity squared. Well, if the denominator is going to infinity and the numerator is not, that piece actually heads towards 0. This is getting closer and closer to 0 as that goes to infinity. Same idea here. This also, this value, as we were looking at that limit going to infinity, goes to 0. And then the denominator, that 2 over infinity squared, that's heading to 0. So as all those pieces go to 0, as we get larger and larger and larger, that y value that we're getting closer and closer to is going to be 1 over 3. So that limit, as x approaches infinity, is 1/3. So we pretty much, this is saying that we have a horizontal asymptote. On the line, y equals 1/3. So let's just take a second. I'm going to pause the video, but I want to pull up the graph of this just to look at the graph and see that as x goes to infinity, we're getting closer and closer to y equals 1/3. I just went to Desmos, typed in the function we were looking at so that we could see the graph of that picture. And so looking at this, notice as we're going off to infinity, it looks like a horizontal line pretty much. And if I look at this, notice that that's going to 0.3, or 1/3, which is 0.333.